So here's where I want to try to kind of convince you that mass and weight, although we use them interchangeably, are not the same thing. So mass, basically, I think of mass as you were able to kind of look at an object and kind of count up all of the atoms or molecules and recognize a certain amount of stuff, matter that was in an object. Weight, basically, you have to step on a scale. Okay, so I'm going to go ahead and we're going to kind of talk through kind of from left to right some different scenarios of a guy stepping on a scale. Now, here on Earth, how's this work? If you step on a scale, okay, basically we have, how do I want to say this? Your feet are on a scale and you are putting a force on that scale. And just like you see in this drawing or whatever, then there'll be a readout of your force. Okay, so when you step on a scale, your weight is actually a force. You're getting the force. Okay, and the way this works is your mass is going to be constant. This is you weighing something. You weighing you. How's that? The acceleration that you're feeling, actually that A is the acceleration due to gravity. So that A there is going to be your 10 or 9.8 meters per second or per second squared. Okay, and then actually we can calculate your weight, and your weight, what your scales say back, is the force. Okay, so that's your weight. I don't know if that makes sense. Okay, you have a given mass, acceleration due to gravity, creating a weight or a force. One thing and actually this kind of made it in the form of a test question on your unit exam, is the acceleration due to gravity on the moon is about 1/6 that of Earth. Okay, so basically this is to say that on the moon, I'll put it over here, weight on the moon will vary. I should say your weight on the moon will be different than on the Earth. Okay, and the reason for that is the acceleration due to gravity is different. Why is that different? Because we have a different mass that we're pulling to the center of. The moon is a lot less massive than the Earth. Okay, I hope that makes sense. Put another way is that your mass on the moon will be the same as on the Earth. Okay. So as on Earth, let's go ahead and take a look at these kind of different figures. So it's hard for you to maybe make out, but I got this guy, and this figure is in your textbook. To me, that says reading, let's round it up to 140 pounds. So actually 140 pounds is a force. Excuse me. Okay, so the next scenario, we have the elevator moving. Oh, by the way, this is the elevator. Okay, this is the elevator moving, but it's moving at a constant speed. Okay, here's the deal. Can you kind of see the rushing up here of the elevator rushing up? So basically, if you've ever been in an elevator, it's that sensation when it first starts that you feel, whoa, and then once it's going, the rate it's going to be going, it just feels normal. And then when it decelerates, you feel, whoa, okay? The wobbliness is when you take off and when you stop. Remember that we said if you're changing speed like that, going from 0 to some constant speed and going from a constant speed to 0, that's called acceleration. So only when you accelerate do you feel the whoa. So basically, if you are accelerating upward, okay, you end up with more of a weight, okay? Your scale would increase. So, for instance, I think this says, let's just round it up to 150 pounds. Okay, why? Because we have acceleration up, okay, and that means we have more of a force connecting with the scale. Okay, let's look at another scenario. I'm just going to go ahead and kind of put these two up because my favorite scenario is the last one, and these are kind of similar. Let's go clear to the last one, and you kind of see the break there. So in this case, some not very nice person, okay, broke the cable, and hopefully the guy at the green hat will be just fine. But when that cable snapped, kind of the frame of reference that the guy was riding in, the elevator car, begins to fall. And, you know, assuming there's no effective air resistance, right? The elevator, the scale, the guy's hat, all fall at the same rate. Okay, it's what we call a free fall. At this point, basically, you don't see the guy's feet on the scales at all. Okay, because why? Because they're both falling to the earth. Okay, and they're accelerating at the same rate. So there's no force there. Okay, so it's free fall. Let's see what else I got here. Okay, so if you were to look up at how much the guy weighs, it kind of dialed down to 0. Okay, he doesn't weigh anything. So speaking of free fall, this is kind of fun. Have you ever seen the International Space Station and seen the astronauts just kind of floating through their cabin? Them kind of floating through the International Space Station is very similar to what we saw just a minute ago with the guy in the elevator that's falling down. The astronauts in the International Space Station are in a persistent state of free fall to the Earth. I'm going to try to kind of prove that to you. Here's a figure from your textbook. I think they do a good job. So I don't know if you can see it very well, but here we have a plank. Okay, somebody built a tower. Have you ever have you heard them talking about building those towers to basically get an object up in orbit? That's kind of interesting. But anyway, so you see the guy that fell, basically he walked off the plank and fell down. Okay? Well, let's say instead of just walking off the plank, he got a running start. Okay? And you can see that instead of falling straight down, he fell a little bit farther. All right. So let's go ahead and let the guy put on a jetpack. Okay? Now, if he puts on a jetpack, and if he doesn't overshoot it, but basically what he can do is what we say insert himself. I love that word, and I'm not real familiar with some of these terms, but insert himself into an orbit. So you see what happens. The reason the guy fell was because of gravity, right? So in this case, he still has that downward component, but he has a this way component, so enough that he misses the Earth as he falls. Okay, let me show you here. Okay, so you can see the little gray guy with the jetpack on his back. Now, and he misses. Okay, so, and remember I said that once an object is in motion, it will stay in motion unless acted upon by some outside force. So once an object has inserted itself in orbit, now there'll be a little bit of friction that they might need to kind of boost up because they'll lose some energy that way. But they should be able to kind of keep going and keep going. So he actually kind of has the residue, I'll try to draw it this way, he has the residue of that original kind of trajectory. Okay, he has the force of gravity pulling down, and this middle one I'm going to show you as kind of the resultant, what we call the resultant vector, kind of between his original trajectory and the force of gravity. Okay, over here he's successful in continuing his orbit. This actually was the direction he originally went, the pull of gravity, and this is his resultant vector. Okay, so he is free falling, but he's moving forward. Okay, so, and he and his, the guy, and if he was in the International Space Station, you know, he would have a little room, that was all. Okay. Now, this is acceleration, remember? Why? Because it's not moving in a straight line. So this guy is accelerating as he orbits the Earth. Kind of an interesting, I don't think we've had a guy in just kind of without any sort of protective spacecraft that has done this. It's interesting, okay? So actually I inserted a slide into your PowerPoint slide, so I need to make this available to you. I don't think I have yet. You see the same picture, okay? And kind of related to that is something called escape velocity. And your textbook introduces it now, and I really think I should too. So I'm going to hopefully play this little animation. Okay. And honestly, I think escape velocity is going to be important, especially when we talk about black holes. I know some of you guys are interested in black holes, but more important to home, I'm going to show you the concept of escape velocity with a cannonball. So I hope you can see this. So basically what I'm going to do here is jack up the speed of a cannonball. I have control over that. I'm going to go to 3 kilometers per second, which is pretty darn fast. And I'm going to say fire. Okay, so it goes out with a trajectory like that. Of course, gravity is working on it too. We have 2 forces, okay, and gravity ends up pulling it and it hits the ground. Well, let's just say it's going a little bit faster, straight out, just kind of like that guy walked off the plank. Let's jack it up to 6 kilometers per second, reload, and fire. It goes further, but kind of gravity wins out. There is no orbital insertion there. Okay, so let's increase it to 8 kilometers per second. Reload. Fire. Oh, I'm liking it. I read the caption down there and it says at 8 kilometers per second. Its speed or its velocity, because we have direction here too. The velocity as it leaves the cannonball going horizontally, it will take about 85 minutes to orbit the Earth, and this is an equatorial orbit. Okay, 85 minutes. Cool. Well, let's go ahead and let's just for kicks jack that up to 10 kilometers per second, and it's going straight horizontal. What's going to happen there? See, slow down. Oh, and I see a caption here. It says at that sort of escape or that sort of velocity, horizontal velocity, it will take 294 minutes to complete one orbit about the Earth. Okay, and it's an elliptical orbit. Okay, and it goes faster. It slows down. Okay, but it's still definitely in orbit at 10 kilometers per second. Well, let's go up to 11 kilometers per second. Reload and fire. Oh, okay. At 11 kilometers per second, straight out horizontal, okay, it will still orbit the Earth, okay, and in minutes, it's going to take 2,350 minutes. Well, I'm not that patient. Okay, let's go to 12 kilometers per second. Reload, fire. Oh, okay. So at 11 kilometers per second, we have this just crazy orbit, okay? The force of gravity would still keep that cannonball coming back. At a velocity of 12 kilometers per second, at this trajectory, it's going to go into outer space and never return. Okay, so 12 kilometers per second is the escape velocity, okay, in this situation. Oh, I think that's all I wanted to tell you in this part.